Oh, now this stream, what we're going to be doing is we're going to be designing an simple image rendering chip. So you can kind of think of this as a GPU, and so we are going to be designing the chip, and it's going to go ahead and it has to go ahead and do all that things. So obviously, we're doing this on Sky 130, and we're going to go through tiny tape out. So. Yes, IKEA lamp. But, so obviously, code is here. So, to start off, we're gonna set up the testing environment, because obviously that's... And zoom in, because obviously, we're gonna be doing this here. We're gonna be setting up a testing environment, right? And so, for this testing environment, it's going to be a little bit more... Yeah, it's Python, right? So, and then... Right, so we have to import quickly. I have to set up the VN, but it's basically just like a quick test that like does stuff. So source dot bin activate, and then from here I'm just gonna pip install Coco TB. Cool, and let's just make sure that that actually works with the tests. Yep, cool. We have a testing environment that works. Cool. So now we have this. What we're going to be doing is we're going to be just putting in our requirements today. So I'm going to be setting up the goals of what we're going to be building today, and I will not stop until it is built. So here we have our testing environment. Right? And so what we're going to be doing is we're going to be doing test-driven development on this, effectively, GPU. Right? And so, yeah, so I'm just going to have this be a master file. So we have, obviously, we're going to make this a little bit bigger. So we will have the format, right? Input format. I'll have this be a multi-line comment. Right, so we're going to have an input format. Boom. Input format, right? So obviously, the type is going to be memory. Right? We're going to have artificial memory here. Right, so we're going to start with artificial memory. And then from the artificial memory, what we're going to do is we're going to expand it, right? So what we're going to do is, since we're going to have artificial memory, it's going to be just it's just going to be a list of just bytes. That's, I don't know, let's set a number. Let's because we have, okay, so tiny tape out. I should probably have this. I'm going to make a new file. No, let's just do this in the README. Let's just do this in the README. This vi thinking dot md. So tiny tape out. Tiny tape out. Tape out. They give us 8 input lines. 8 input ports. Wires. I'll say wires. 8 input wires. 8 output wires. 8 bidirectional wires that you can have for both either input or output, right? And so the 8 bidirectional ones basically have 8 wires for it, and then 8 selectors basically that select whether you're using them for input or output. So you can effectively control each one, right? So what we're going to be doing is theoretically, right, we have to decide our input and output format, right? So theoretically, our output, right, is going to be going to a point in memory, and it's going to be having the sort of like memory address of that point in memory, right? And so it's going to be the RGB value, right? And so the RGB value is going to be 3 8-bit values. So 24 bits. Then what it's going to be is it's going to have a memory address. And so let's theoretically have this render image format. So let's have this image format. Let's do something small, right? Let's just have it be 128 by 128. 256 by 256. 256 by 256. It'll be slower, but like that's whatever. We can deal with the perf issues, right? Cool. So 256 by 256, 8-bit RGB. Right, so that's our image format. And so theoretically, this is going to be 2 to the 8, 2 to the 8 plus 8 plus 3. So each image is going to have like, in terms of total amount of memory space it needs, is going to have 2 to the 19 bits of memory, right? So this would be all like 512K ish. It's going to be a 512K image, right? Just pure this. That's big. We're dropping this down to 128 by 128. Theoretically, we can scale this up, right? So this would be 7, 7, 17, and so divided by 4, this is going to be roughly a 128K image, right? So it's a 128K image, 17 bits. So we're going to have, because the nearest multiple of 8 for this is going to be, we can go to 24, yeah. Okay, so it's going to be 3 bytes. So memory address is going to be 3 8-bit values, right? 24. It's just going to be a 24-bit value. It's going to be 24-bit address, right? We're going to do 24-bit addressing. This is going to be a slow thing, right? Like, because again, 128 by 128, 2 to the 14. Assuming we're running this at, like, let's say 20 megahertz, right? So we're going to be running this at 20 megahertz. Well, that's like an image a second. That's like not that bad actually, because this is not that many pixels. We can probably run this at 24 FPS. You know, place Snake at 24 FPS. Bits, right? 24 bits. And so this is 48 bits. Now, obviously, we can do this simultaneously. So it's going to take us 3 cycles to actually output a value, right? 48 bits for one output. And so because we have 8 bidirectional wires, what we're going to do here is, because we have, again, 8 bidirectional wires, we're going to have, during output phase, we're going to have it do 16 outputs, 8 inputs, and these are mandatory, right? So cool. We have 16 outputs and 8 inputs. Amazing. Then what we're going to have to do is we're going to, so we're going to have during the input phase, so I'll have input here because input comes before output. During the input phase, where it's just like reading through the sort of memory. So let's just split up memory. So we have effectively a 24-bit address, and so we split it up into the first memory layout. We're going to have the first bit. Right, this is an MD file. We're going to have the first bit, which is going to be our input area. That takes up that goes from 0 to 2 to the 23, or I'll just write this in hex. So it goes from 0 to it's just one. Well, so 0, 1, 1, 1, which is 7. 0 to 7, F, FF, FF, and I'll deal with the format later. And the output area, which is our output final image, is going to go from 0x 8, 1, 2, 3, 4, 5 to 0x FF, FF, FF. Right, I should probably do 0x 0, 0, 0. Cool. Right, so this is our input and output areas, right? So it's just the first half of memory is going to be all for inputs, right? The second half is for outputs. And then for inputs, what we're going to do is we're just going to have I will treat this as like a stack of, I'll treat this as a sort of stack of 2D, what's the word? 2D shapes, right? So we can be like, hey, this is a triangle with the 3 vertices. Here's a square with 4 vertices and whatnot. Here is a circle, right? And we have all those calculations in the chip. And so, yeah, we have the input area and the output area, and it's a stack of 2D shapes. And it's just going to go shape by shape by shape. And if the shape is in, so because we're going to be going output pixel by pixel, and we're not just going to be like, apply the shape, apply the next shape, apply the next shape, apply the next shape. Well, that's how we're going to be defining it, right? But because we have our outputs, what we're going to do is we're going to have the stack of 2D shapes, and each shape is going to have, its own bounding box. It's going to have its own, so we as software developers will define the bounding box of the shape for like, hey, do we check here or not? It is going to have its own color. It's going to have a type, and it's going to have necessary data for the type. And I don't know, let's limit this to, let's say each vertex is going to be 2 pixel positions. Let's say each of those are 8 bits long. And then, I guess, that's a massive output here. Anyways, each of those is going to be 8 bits long, and so that's 2 vertex, and let's say we'll support theoretically 4, so that's 8 bytes. So the bounding box here, we know it's a box, and so we only need 4 numbers, right? So left side, right side, top, bottom. So 4 numbers. Each of these is 1 byte, so 4 bytes. The color of the shape is, again, as we said before, 3 bytes. The type of the shape is, we can set it to be whatever we want. 8 is just 256 different shapes, 1 byte. Right, we're just going to do this byte by byte, as we do. And then we're going to have the necessary data for the actual rendering. And so the necessary data is going to be, how much? Okay, we could go with the whole, you get 4 numbers, but that's 2 vertices, right? So that's 4 bytes. Let's go with 16 bytes, right? We're going to be reading a ton of data, right? Not very data-intensive process. Now, obviously, we have the input limitations where we can only have 16 at a time, so we can only do 2 bytes, right? So we can do first half of bounding box, second half of bounding box, first 2 bytes of color, last byte of color, necessary data, right? Cool. And so we're going to be going through all of these things for every. Yeah, that's not great. Oh well. The goal is 1 picture per second, right? I should probably write that down. The goals, right? Goal: 1 picture per second, right? Obviously, if we have more shapes, it's going to increase the amount of pictures, right? 1 picture per second. No, let's go a little bit faster. 60 FPS with, let's say 128 shapes. Right, so we're going to set perf targets, right? We're going to make a 60 FPS with 128 shapes. And, yeah, at 128 by 128, right? So the goal is 60 FPS. Maybe we'll run this at 60 megahertz, and so we just have 1 megahertz to go, but it'll probably be less in terms of total cycles. Though, if it takes us 500,000 cycles for one thing, it's like, you've done something terribly wrong, right? Though each output pixel is going to take 3 cycles on its own, so. And we have 2 to 14, so that's 16K. So that's 48K cycles already. Just on output. Okay. Oh well. It is what it is. Cool. And so because, in essence, we can optimize this because we just go from the last point to the first. And so, there's some optimizations we can do there. It is what it is. Cool. So, we have the bounding box, we have the color, we have the type, and we have the necessary data, which I'm going to give 16 bytes to, for like, hey, you have a triangle, 3 vertices, each vertex is going to be 2 bytes, and so that's 6 bytes there available for you. And so obviously if we detect the type as like a square, and we are like, just use the bounding box then. We can just ignore this and like add 16 to like the header or whatever. Or like go to like, what, hold on, this is 8 plus 16, 24. Yep, that's sick. And so, only the last shape will show, right? And so, yeah, so basically only the last shape will show. Yeah, so we just have to read it from, So read the memory from last shape to first. Right, and so the start of this area will be general info, right? And then, and so this will include stuff like where, so there's like how many shapes do we have? Yeah, it'll have stuff like how many shapes do we have? That's kind of it, whatever. And this will be a number, let's say, not 256, 16, 4 bytes, yeah, 4 bytes. 2 bytes. 2 bytes for how many shapes do we have? Also, 1 byte equals 8 bits here, because again, that's not necessarily standard, right? 1 byte is 8 bits, and so, yep, as we do. Cool. And so then from here, we have the output area. Yes, so the 1 cycle is 48 bits. And so, yeah, so the input cycle will basically just, so read the memory from last shape to first. Once we find a shape on our pixel, we stop and display that color. Cool. So we've defined the shape of our memory, and we've defined our output area. And so now what we have to do is we have to, yeah, figure out what we're going to do at the start, right? All we're going to do at the start is, again, the goal, as you can see at the bottom, is read from memory and output. I will edit the text here. Output 1 shape. Okay, so what we're going to do is 1 shape. We're going to have the start of memory be 1 shape. Cool. Now let me edit the tests, right? Nvim test.py, right? So we will call this 1 shape test, right? So it's going to I'll leave that there, whatever. So we're going to set the clock rate to 100 kilohertz. This doesn't actually matter that much for us right now because we don't particularly care, but it might, yeah, eventually. So we'll just leave that as there. So we start the clock, we do the resets, we let it reset, and so we're going to do read start of memory. Sorry, read start of memory with 1 square. Let's start with just a square, a simple rectangle type square, right? So all we have is the bounding blocks. 1 square in the middle and display it. Right? Cool. So, cool. So, what we do is first we're going to set up here memory. So I'm going to make a function here. Def I'll make a memory class. I'll make this a class. Class memory. And so we're gonna have the init. We're gonna have the init here. And so the init will have self, and this is just going to create like an empty massive amount of memory for us. Right? So mem equals memory. Cool. And so then in this init, what we're going to have is we're going to set it up so self dot input. So the input memory is going to be, it's just going to be zeros for 2 to the, we agreed, nvim.this/, thinking.md. We agreed it's going to be, the input format is 0 to 2 to the, what is it, 2 to the 23? 2 to the 23 bytes. So 0 for I in range. No, we're just gonna have it be just a small set here, and we can just set up the size. Self, comma, input size, output size, right? So the input will be 0 for underscore in range. That's an O, not a 0. Whoops. 0 for underscore in range input size, and output in range output size. Cool. So we can just manually set up here. So the input size here, at the start is going to be one thing, which is 24 bytes, 24, one bounding box square, and the output size is going to be, let's say, 4. Let's just, it's 128 by 128 times 3. I don't want to set up the, I could set up the 128K. Okay, cool. 0. What is, hold on. So it is going to be, output area is, it's not 2 to the 23, it's 128K, 2 to the 17. Okay. And so here we're going to have 2 to the 17 bytes, right? Because 3 times, yep, 2 to the 17. Hold on one second. It's 8. It's just this number times 3. So it's 2 to 14 times 3 because it's 3 of them. Okay. So 2. And there's a 64K. Cool. There we go. That math was 2 to the 16 amount of memory. 2 to 16 bytes. Cool. And so there's a memory. And so then what we do is we effectively, how do we want to input this, right? So the first cycle, we're just gonna have this ask for, okay, how are we gonna do this? So it's reset, reset, reset. Next, we turn reset off, right? So we are no longer resetting. And so the input value, it won't care about it. It will just set up the output value. UO out value, right? So the dedicated output is going to give us bit 1 of the memory address we want to read, right? So it's going to give us 0, sorry, byte 1, dut.uio out dot value is going to give us byte 2, right? And then obviously UI, and then we're going to assert, right? We're going to make a check that UIO enable dot value equals 255. Let me check if, hold on, where is the docs? Yeah, UIO out, text specs, GPIO pins, UIO, it's bidirectional, right? Is 1 an output or is, okay, yeah. Where is, come on, guys. Test readme, nope, nothing here. Okay, that's unfortunate. I'm just going to assume that one TTUIO tiny tape out. Okay, let's read this. UIO by default is 24 additional clock. Yeah, you can put it in, whatever. Getting started. Where Okay, we will figure that out at a later point in time. Though I guess I realized because we're doing like behind or above you. What? Okay, sure. Deal with that later. So it's okay. I'm just gonna assume 1 is for I'm gonna assume 0 is for read enable, right? So we're gonna cert. So I'll set up a comment here. I will set it up so it's going to say that we're going to have chip asks for the first. Yeah, chip asks for first value. Yeah, first shape. No, we want to do the last shape. So hold on. So first we're gonna set up chip asks sees number of valid shapes, right? And so it asks. So obviously this isn't gonna be 24. This is gonna be 25, right? Because 0 will contain the number of shapes, which is maximum 256. Okay, what did we set it as? General info, 2 bytes. We said it as theoretically we can have 16K. Okay, 2 bytes. Cool. So the chip sees the number of valid shapes. This is going to be 2 bytes, so 26. And we're just going to have 2 to the 16. That's a lot of memory. That is a lot of memory we're doing here. Okay. Interesting. Very, very interesting. So we just have to figure out, because we have memory here, we have to. The chip sees the number of valid shapes. Okay, hold on. So we're gonna start by. Let me make a helper function here. Def read from memory. We're going to take the DUT, and then we're also going to take the memory object. So read from memory, and then we also have to find out the address, right? Which I'm going to say is an int. And then I don't care about type checking here. This is a test thing. We're going to take the memory address, and we're going to take the data that we are reading from memory. Cool. And so this should be us saying this should be reading from memory. So this should be 2 equals. Cool. So we're going to be reading the first bit of memory data, and then data size, right? How many bytes is it reading? Yeah. Cool. I'm using K as in the kibibytes, not kilobytes. It's 64K. 2 to 16. Cool. And so so we have the chip. It has the valid. So we see the number of valid shapes. So we're going to do. Hello. Why am I in visual mode? Yeah. Okay. We're going to see the valid number of shapes. So read from memory. So we're going to feed in the duty cycles and whatnot, and then we're going to feed in the memory, and from there what we're also going to do is we're going to feed in, so the address is going to be at 0, the data is going to be 0, and it's going to be 2 bytes. Cool. And so then from here we're going to read from memory, so we're going to set the read from memory. We're going to have the UO out. Oh, that's an assert. Okay, so we're going to assert UO out is 0. We're going to assert DUT dot what is it? Yeah, DUT dot UO out dot value. We're going to assert DUT dot UO out dot value to be 0. We're going to assert DUT dot UIO out dot value is 0. We're going to assert DUT dot UIO enable. I'll just have a variable here. Enable. I'll say output enable equals 0, input enable equals, this would be 255, cool. UIO enable, we're doing output here, so we're going to set this as output enable, cool. And then from here, we're going to run the clock, and so we're going to just do an, oh wait, this has to be an async function. Await dut dot, I'll just yank this. We're going to do 1 clock cycle, right? So we're going to go full clock cycle, and then this memory, this data has been read by the memory, and then we're going to yank this. So this is going to be byte 0 of the address, byte 1 of the address, byte 2 of the address, unused. This is just enabling it because, you know, we have to enable it. Cool. And so then from there, what we have to do is we're going to await another clock cycle, right? Give the other end time to handle this stuff. And then what we're going to do is we're going to say dut.ui in. I can just set that. Yep, ui in dot value, and we're going to set that to be data, but it's only the first little bit. Okay, so we're going to put this in a for loop. For yeah, okay, hold on. We'll have this for underscore. I use I in range. For I in range, data size. We're gonna first have the CPU read the data, and then say the address we want the data to be in. Then I'm gonna say dut.ui in.value, and we're gonna set that value of this to be we'll just set it to be data, and we have to right shift it by I, and then after we right shift it by I, we're gonna slap off the rest modulo 256. Cool. So there's the data we fed in, and the chip will go take the data, and we're just gonna have like discrete input cycle. So this is gonna be a discrete output cycle, and this is gonna be a discrete input cycle, right? And so obviously we're gonna be reading this 1 byte at a time. So we're gonna have 3 cycles per byte read, and so yeah, and then we do a clock cycle, right? So we have the discrete output cycle, and then we have the discrete input cycle. And great, so now we know that we've read the data. Okay, so this value should be the byte 0 of the address, so address, the last 256, address, right shift by 8, and then obviously modulo 256, right? And then same thing for here. This time we right shift by 16. So address right shift by 16, modulo 256. Right, cool. And so then there we go. And obviously that one's unused, so we'll just leave that as 0. Though I guess theoretically we could support 32-bit addressing, but meh, whatever. And so yeah, we have the UI in dot value that we're feeding in. And there we go. And we have our certs already, not double equal, this should be a single equal. Cool, and memory is obviously just not going to update. That's just going to be your assumption. Memory, you tell it you're reading data, and it's just not going to update it until after it. Oh, we can set this to be the read-write byte. Yeah, I'll set this to be read-write. Read-write. And so this is our read-write, so the value here is going to be the input enable. We're reading, yes. Input enable. My 255 is going to be we're reading all the memory data from memory, and then, right, because we're inputting into the CPU, and then, yeah, and so the write is going to be the, yeah, cool. So I'm going to yank 20. Please tell me nothing crazy. Yep, nothing crazy happened. Cool, and so then this is going to be our output. And so this is going to be output to memory, right? Output to memory, and so we give it the address. We're telling it we're outputting to memory, and then from there, what we're going to be doing is we're outputting 1 byte. So dut.uo out.value, and we're going to be asserting it's 1 byte, so it's just going to be straight up data. We don't care about the data size here, because again, this is going to be byte by byte. I want to be able to support being able to do this multiple times, so obviously, right, we have to do. It's going to start with the address, and then byte 0 plus I, right? So there we go. This plus I, and then hold on. I'll set up a mem address equals address plus I, and so this is going to be the mem address, memory address. Cool. Mem address, just so we can handle multiple bytes in a row. Cool. So we have the memory addresses, we have the clock cycles, output UO out. We have to assert value equals data. We should not be setting up data here because we have the memory, right? Yeah, this should be read from memory. So we should just straight up read memory dot. I mean, memory is just a stack of things. Hold on. Data. Okay, cool. So we're gonna have, and then obviously to start this, I will just set mem dot input, because we're reading entirely from the input section, right? All our inputs in the input section, we're not writing to it, and the output section we're only writing to, right? So mem dot input of address of mem address equals data right shifted by, not by I times 8. Data right shifted by I times 8. Modulo 256. Right, so this is just, hey, we know if this works, we know we get the right transaction, and so we will do the right transaction in memory. And so here, mem address, yep, this is correct. And then here, the output val is going to be, so it's going to be data right shifted by I times 8, modulo 256, modulo 256. And then this is the point when this is read from memory. Data equals mem input of mem address. And we're just going to be checking for data here. Cool. And then here's we have output. And so we're going to say mem dot output of address minus, sorry, mem address minus 2 to the 23. Yeah. No, not minus. It's right shift. Right shift 2 to the 23. What am I doing? It is minus 2 to the 23. Minus 2 to the 23. Cool. And so we're going to set this to be this data bit. So I'm going to yoink that. Yoink that. Paste it in there. Cool. And so there we go. So I'm going to say, hey, read this from memory. Output this to memory. We're good. Cool. So we have obviously the output state 1. Sorry, the input state 1, input state 2, input state 3. And then we have output state 1, output state 2, output state 3. And yeah, so, and in between we're going to have a bunch of states. So I'll write down the states that I'm thinking of for the state machine, because I'm already doing this in the state machine. And so, yeah, so chips, we no longer have that. So data size of 2, we're reading in address 0. Cool. Memory starts with a whole bunch of zeros in there, so I need to fill in the data that we want in memory. So obviously, mem.input of, and I'll just like manually write it in. So we go 0, 0, right? That's byte 1. This would not be 0, 0, this would be 0, 1, right? This is, there is 1 shape in memory. Then we have shape 1. And so for shape 1, what we're going to do is wait. Yeah, cool. And so for shape 1 is going to be just, we're going to start with the bounding box. So I'll just say, because our thing is 128 by 128, we're going to have the left edge of it be at 32, and the right edge of it be 96, and then 32, 96. So X left, X right, Y top, Y bottom, right? And we're going to have top left is 0, 0. There is bounding box at from 32, 32 to 64, not 64, 96, 96. Cool. Then what we're going to do is we have the, yeah, and so then we have the bounding box, and then we have the color, right? So the color of this, let's just set the background as black, right? Default background fully black. And so I'll just set the output of this to be white, so it's going to be 255, 255, 255. RGB color. And then after this, what we're going to do is we're going to have the, what's it called? And then the extra data, which is empty for this one. How much data did I, well, I know it's 24. And so we have 1, 2, 3, 4, 5, 6, 7. And so, wait, 7. Oh, and then the type. Type, let's say 0. Right? For the fact that this is a, I'm not going to use rough. 0, this is the shape, not shape. This is the type. And so this one will be a rectangle. And then after that, now we have 16 of 0, so I can just do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I'll split this up into 4 lines. And I'll just have a comment being like empty. Empty. Yank the rest. Cool. I'm gonna space this out nicely, just so it's like nice to read. Type of the rectangle. I should probably have a nice helper function for this, but this is the one test we're gonna be doing today, making sure that this works. We can have one thing, right? So we're gonna read the number of valid shapes, and today we're gonna throw that out, but later we're gonna do some calculations on it. Next, we're going to go one more cycle, right? I guess. This one it's already read it, and then now we have to figure out. Yeah, so we're gonna read the next shape from memory. So we're going to read starting from memory address 2. We're gonna read the next 4 bits of memory, right? So we will go, and then once we read this, we should probably have an extra. Yeah, so it figures out the data, and it like stores it somewhere, right? We keep track of it, and then we have to read the next bit of memory. We'll figure this out later. So this is Chipsy, Chipsies, and obviously we are just going to be dealing with this. We'll read the bounding box. We're going to read, and so then this is obviously going to check, because obviously we're at choose number of valid shapes, and that's going to stay constant. So then for x in range 255, for y in range, not 255, 128. What am I doing? 128. Right, so we're going to do the chip checks the first shape, so it reads the bounding box. It'll see that we failed the bounding box check, and then we're going to write to memory. We're going to write a. I should probably have the check here. Yeah, so I'll comment it later. If x less than 32 or x greater than 96 or y less than 32 or y greater than 96. Let's just say the bounding box is inclusive on all of them. We're gonna, well, obviously we're gonna read from memory, right? Because this is how we know the bounding box. Right, so we're gonna read all 4 bytes from memory. Then what we're going to do is we're going to write to if it's wrong here, we're gonna write to memory, right? So dut mem address of 2 to the 32 plus, let's say x is the small one, so it's going to be 128 times y plus x. So, right, so that's the address. Then we have the xyz. I mean, we're writing 3 bytes to it anyways, right? So, yep, data size. So data, we're gonna write 0, 3 bytes. Else, we're gonna write 255 times 3 bytes. Cool. And that's a test, right? Cool. And so then make dash b. We should expect us to fail a test. Yep. Oh, we failed a test. Oh, we can't. I'm bad. Whoops, forgot about how Python worked. Single shape test. We're gonna make dash b, and we failed. Right, write to memory failed. Hello, read for memory. Memory address. Address plus I. This should fail. What? Oh, I have to await this. Whoopsies. We failed in read from memory. Nice. So, byte 2, we should be reading. That's the wrong read from memory we should be failing at. We should be failing at the first one, right? Because we're theoretically reading 2 bytes. Right, we're reading 2 bytes, and 2 bytes. The second byte is this should be 1. Right, address. Yeah, we're reading 2 bytes. It should be 1. So 1 modulo 256 should be 0. Yeah. So it should be 1. So that should be failing. I'll have a print. I'll have this print. Print. And obviously this is going to be formatted. Memory address read. So mem address. I'll just keep it big, whatever. Warning. Why is that a warning? Oh, I should not be doing print. It should be dut dot underscore log dot info. Dut dot underlog dot info. Cool. Just CocoTB maxing. Memory address read 2. Why are we reading address? Oh, address 2 is the failing one, yeah? Yeah. Right, cool. What? 0, 2. Oh, the first one wasn't awaited ever. That would check out. Yes, we have to await this one too, right? Asynchronous. UIO enable equals output enable. Cool. So I will. Now we have a test to do. So cd src nvim project.v. There we go. So right, we have active high. 0 is input, 1 is output. Great success. I did remember that right. Always want, yeah, so we can ignore this, reset and load to reset. Cool. So obviously these don't matter. So I'll have a register, and I'll have, I don't know, an 8-bit register. That's just our current state, right? And so then we will also have a few others. So we will have a register that's 24 bytes long, and this is going to be our address that we're going to be checking. We're going to have a register that's, I guess we only really care about the color data. Yeah, so register 23:0. So this is going to be our color info. Then we're going to have a register for the current pixel. So this is going to be 2 bytes. So this is going to be 15:0 for this is current pixel chords. And so, yes. And so then, yes. And so I'll just set up the state stuff down here. Assign at always, yep, at pause edge of the clock. Begin. End. Right, so if load to reset, so if rst underscore, so if it's low, we're gonna reset it, right? So we're gonna set hey, the state will be 0, the address we will be checking will be 0, the color we are checking will be, the default color is there, 0, doesn't really matter. The current pixel will be 0. Cool. And obviously the end. Cool. Then we have the else begin, and this is where we actually do stuff. Cool. Now I have to figure out the next thing to do, right? So to pass at least the first reading thing, right? So we begin. So how to Verilog state, find state machine. Amazing. Yeah, cool. Current state. Right, we have to have a next state. Nah, the next state is just implied with this, right? So whatever. We're having current state. Yep, next state. Cool. next state. Yeah, case. That's how we do case statement. Case statement on state. Okay, and it's just state name. Cool. Read one. Begin. End. And so the read one, we already have our address, right? So we're going to, yeah, we're just going to output address of 0 to UO out. So, oh yeah, reg UO out reg. So this is the register we're going to have, and this is going to be another 8 bits, 7:0. This has to be 255. Bang, bang. And so this is going to be UIO out reg. And so this is going to be assigned. We're just going to assign it to the value of UO out reg. And this is going to be the UIO out reg. Cool, amazing. Now that we have the output and UIO output and we've enabled it, cool. And so, yeah, so read one, we're going to set UO output, UO out reg. So read one will be, I'll just use numbers here because it doesn't particularly matter. We should probably label this later. Yeah. So UO out reg will be equal to address of 7:0. UIO out reg will be equal to address of yeah, so it'll be equal to address of 15:8. Then we're going to have state 1. Oh, and then obviously state will become 1 after that. I'll just have a comment here. Read double slash read 1 begin and how about yeah, okay, it is what it is, right? So this is the starting one, so I need to figure out how we're going to do a state machine here. So that's going to be a lot for this first stream. So hold on, let's simplify the goal. We're going to read the number of shapes. That's all we're going to do at the start. So read 1. How do I set up a constant? Constant in dialog. A parameter. I don't want that. Local parameter. No, I just need. Yeah, there we go. Backtick define at the top. Cool. Okay, sure. Backtick define. I don't know. Let's set read num shapes 1. We'll set that equal to. I can just do that. And so here, read num shapes 1. And so obviously address is 0, so this is our default state. This number should not change in the running of our program, right? This is just a constant at the start of memory. And so obviously I can leave that there. And then yep, and then going that comment because this is the comment enough. And then 2 will be 1 here. We have 255 states available. We can go crazy here. Paste. Yep. And then here we're going to set this to be 2. This will be 0. And the address here will be, yep, address of 23:16. Right. Cool. And so now that all of these are in, this state will now go to state 2, which is actually reading in the num shapes, which is a constant that we care about. So reg 15:0 num shapes. Yep. And so the number of shapes we have it here is going to be 16. So we're going to backtick define, and this is going to be the read num shapes 3, and this is going to be state 2. Yep. Yank 4 down. Yep. And so you read num shapes 3, and we're going to begin there. And so and so we don't care about these registers. We're just going to set num shapes is going to be, you know what, I'll just have this, we're going to start with this being just 8 bytes because I don't want to have this go through 2 cycles for that. Num shapes, and we're going to set that as equal to UI in. I can just, yep, UI in, dedicated input. And the next, I should just say, next state should be read num shapes 2. Read num shapes 3. And so obviously, now that we've read the number of shapes, we will have this be read, and obviously because of after this, address should be set to, because that's the next thing we're reading, right? So the address should be set to UI in, so this is the number, times 24, because that's the size, plus 2, and then obviously UI in minus 1 times 24, right? Minus 1 times 24 plus 2, right? So this is a constant. It'll optimize away. We're chill. Right, so that's the address of the first, this is the address of the first shape. We want the address of the last shape, but we will deal with that later. That's a problem for later. Read shape 1. Right, so this is the reading of the first shape. And so what we're going to do is we're going to be, yeah, so we're going to do another 3 for read shape. Read shape is going to be very long. Backtick define read shape 1. And so this is going to be 0, 2, 3, so this is byte 1. We should be doing this 4 times until a counter, so I'll just have a register that's, I'll set it to 8 bytes, 7:0, 3:04 bytes. We don't need more than 16 bytes for anything of counter, right? We'll just have a random counter, and so then bang, there we go. And here I set counter is 0, and then here, yep, cool. So here what we're going to do is this state, if counter is equal, so we start at 0, then 1, 2, 3, right? So if we see 3, that means we've gone through 4. So if counter is 3, the state will go, oh, that's at the end. Hold on. This is going to be read shape 1. So read shape 1, right? So obviously paste this in and y4j, and then obviously we go to read shape 2, always read shape 2, and so I can just yoink that down here, and then read shape 3, right? So this is bounding box, so I'll just call this bounding box, and then here this will also be bounding box. Cool. So read shape bounding box, 1, 2, 3. Process line s slash read shape with read shape bounding box, and then just apply it all. Cool. So, and so obviously now we're in read shape bounding box 3. Okay, whatever, that's going to stay highlighted. And so here, what we're going to do is we're going to have counter. I did call it counter, right? I did call it counter. Counter. And I'm going to say counter plus 1. And this will, and so then if counter is 3, begin right, and then end and what is this? Else begin, and so this else will take us to reshape bounding box 1, and the address will be address plus 1, right? Because we're reading the next one. Cool. And so then 0 is read. Yup. 3 we don't care. We want bounding box. I'll set 1 for bounding box. Reg 23:0 for our bounding box. This is a crazy amount of registers for the area we're taking up, but you know, we can cut it down later eventually. Right, so we have the bounding box. Cool. And so then here we have bounding box of, and so this will be from the high end, so this will be counter times 8, right? So if it starts at 0 plus 7 to counter times 8, and so that's the place we're going to, and this will be written into by UI in. Amazing. Cool. So now we have the reading done and ready in theory, and so now let's test it. Right, just see all our signals correct and all our timings correct. We have compiler errors. Cool. So line 41. Line 41. It's down here. Oh boy. Add Verilog. Always at pause edge. Always block. Always at event. Can I at pause edge? CLK begin. Always at. Do I need a space here? Pause X. pause edge CLK begin. What is the problem? What? Okay, hold on. Oh, so always at the positive edge of the clock. We go into our state machine here. And so what we're going to do is, yeah, so always CLK, input wire, yup. Not used and assigned to 0, yeah, okay. Okay, let's just invalid module instantiation 40. Okay. SOC project V. Okay, let's just go down to line 44. ADDRESS. Okay, what's the problem with calling an address? Invalid module instantiation. Mem address. Percent sign S. Percent sign S slash address slash mem address. Just apply to it all. Call it mem address. 44 invalid module instantiation. Okay, so this is probably all syntax error based. So 41 has a syntax error. There's a syntax error here. Always at pause edge clock begin. Okay, hold on. Let me move the begin to the new line. Let's see where it starts. Still 41. UIO OE. Yep. Assigned 255. Assign. Oh, unused clock. Long unused. That's not unused. We're using up all this stuff. Yep, still here. Okay, so now we're in syntax nightmares. SRC 41 and then 45. Okay, 45 is still the mem address line. Where's all the others? 44, 40. Okay, so 44, 45, 46, 47, 51, 52. Okay, there's something wrong with my writing of the word state here. Because this if is not throwing it out. No. Huh. Follow the V44. Yeah, okay, so effectively this is... Yeah, this is effectively a keep going. Okay. You know, today I will make sure the reads work. Read from memory. Yes, I... Rename. Not rename. Hold on, let me edit the goal. Yep. Read from memory. The goal has been shrunk. We're not going to go for many, many, many hours here. Because this syntax error is actually kind of annoying. So, let's start at the top. 41. 41 is here. Let me move this to the bottom. Hold on. Let me just move these to the bottom where I believe they should be. Cool. So everything else moved up. So that's a good sign that it's all in this stuff I wrote. 38. It is this line. Yeah, this is 38. Always at... Oh my god, the at should be out with here. That's annoying. Oh, the stack size went down. Nice. Amazing. Default net type none, yeah. We want, okay, so my defines were bad. Cool, got it. Line 60 has an error. It's a forgetting of a semicolon. Yeah, it's basically just the defines here. Do I need an equal? No, line 20 still has an issue. Wait, line 20? Do I owe OE? Huh? Okay. Verilog, backtick define. Backtick define. Ask me in a week. No, this is correct. Backtick define something. Yes. Okay, this should work. What is the problem with UIOOE and then going down? This is like auto-generated. Why is the auto-generated stuff having compiler issues now? Oh, default. So I move this below. Okay, sure. What? Move these up back here. Cool. And then, okay, so same errors in same spots. Malform statement, incomprehensible. How? This code was auto-generated. What? Home, image rendering. Yeah, okay, so now we just have to figure out the incomprehensible case statement type stuff. But, yeah, Huh. Okay. How... Okay, how am I going to pull this off? That's the immediate challenge here. Because... Yeah, Lesson syntax. Default net type must appear... There we go, default net type. I'll put it all the way at the top. Oh, line 80 has the... Well, now it's 86. What is line 86? Oh. We ended that. We ended that. Do we have to end the full-on case statement? Right, so we ended that if. We ended that. Okay, hold on. Verilog case statement. Oh, I need to write end case. There we go. Okay, this indentation is wrong. Because this whole indentation is wrong for whatever reason. Sure, whatever. Oh, amazing. Unable to bind line 51. I assume it's this. No. Unable to bind wire reg memory num shapes 1. We're not binding it. It's just a number. Case statement. Not right. I just need like a number I can use. Bruh. Okay. Verilog constants to use in switch statements. Cool. So we have parameter blank equals blank. Oh, that's exactly what we need. Cool. Colon s, and then it's going to be backtick define. We're going to replace that with parameter bank, and then here I'm just going to manually enter 0, 1, 2, 3, 4, 5, and then yoink that all in here. I should have find and replace that, whatever. Next error, line 65. Unable to bind all of this stuff. Bias rule. I'll deal with that later. Okay. Unable to bind. What? State idle, stuff happens. Do I need a default state? I guess I probably should. And if count is 3, we get stuck here, and it's like, whatever. No. We should not get stuck here. For, I guess bounding box 3, if count is 3, we get stuck and we deal with that later. Default case. State will go to 0, which is whatever 0 will be in that case. Cool. This should just work. Colon begin. Local param. Local param of fix a compile time. Yeah. Cool. Width should match. Yeah. Cool. Oh, I can't just say 0. I have to say 8. Backtick. Hex 0. And the first one 65. 65. Okay, this is getting minorly annoying, and yeah, 8 apostrophe process. It should be no state is 8. Yeah, 8. Should I just put that at 0? 65. Oh, that wasn't even the issue. Hold on. Read num shapes 1. Okay, it's bounding box that's the issue. Read shape bounding box. Read shape bounding box. Bounding box. That's the issue. That was truly amazing. Great success, me. Cool. Line 79. Counter is not allowed. I can't use counter in there? The LSB violates the rule counter times 8 plus 7. Okay. What's the max of counter? 2 bits. 79. A reference to, oh, it's not allowed in a constant expression. Dang. Why? Am I just not allowed to be super clever? Times instead of times 8, left shift 3. A reference to a wire or register is not allowed in a constant expression. Does this have to be a constant expression? Oh, come on. Oh boy. If counter equals 0, begin. End. It's going to be 7 to 0. I love this. 7 to 0. Else if counter equals 1, begin. Yoink. Paste. Paste. Counter is 1. Counter is 2. Counter is 3. And add a little bit of space. And so 7 to 0, and then we go 15 to 7, 15 to 8, and then we go 23 to 16, and then we go 31 to 24, and there we go. That worked. And then the issue comes here. Why did this assert fail? Memory address read 0. Why? Oh, we should be reading 1 byte, presumably. Yeah, okay. Hold on. Well. Cool, so nvim test.py, and so then here we should really only be reading 1 byte. Cool. Memory address read 0. So on the first one we're failing because UOut value should be memadd mod 256. Why is that an error? Let's just print it out. Let's print out UOut val. And this would be dute.uout.value. It is undefined. Nvim because uooutreg. I see. I see. Num state. We need to give it another cycle. Well, first, what we need to do is we need to set uo out reg to be 0, uio out reg to be 0. Cool. Okay, where are we failing? UIO out enable should be output enable. Why is this? Yeah, it should be output enable. Yeah, 255. UIO OE 255. UIO enable. What is it called? UIO OE. UIO OE OE OE, and then here it will be OE. Cool. Assertion error. UO outread. Okay, UO UIO output enable. UIO output enable. Cool. One, two. What? Why is this an issue? We're checking if. Do I have to manually set it as? Do I have to go int? Oh my god. Please tell me that this is not the secret solution. That was the solution. Your out dot value. Line 24. Why is this the problem? Oh, right, because %sign s colon %sign s slash dut with int dut slash gc. No, 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 no. Yes, yes. No, no. Yes, yes. No, no. 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 Yes, yes, yes. No, yes, yes, yes. No. No. Oh, I have to do that. Now I can do this one by hand. Cool. And so then here. Bang, 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 bang. UO out dot value. UO out value is 0. And we're checking if it's equal to 1. The address did not increment. This is because we should have. The problem is the output here. When you throw in an extra wait cycle at the end of each byte, yes. No. Use int dot val. Oh, boy, okay. Yep, I don't want any of these warnings. Cool. And I'll do that on the right one later. Okay, so the problem is the timing's off here, which checks out. Okay, let me add a delay at the start. So the first one, that one worked. Why are we reading crazy number? Memory address read 1. We should be reading address 1. Why are we reading crazy number? Project.v. Okay, cool. So now, oh, fancy colors. We go here, 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 and then here we should be good. Num address is a crazy number here. Yeah, that checks out. I will just manually set it to 2. This should be 1. Hey, nice. We were able to read data from memory flawlessly. Warning, write to memory is not defined. Nvim test.py. Output to memory. I call it output. I call it write. And the writing will fail. The writing will fail. We are able to read 0, 1, 2, 3, and memory address 4. So this is where our bounding box is, right? So if you remember, yes, it worked. And so yeah, so we're able to read where the bounding box is, and so theoretically, now we should be able to check to it. So read from memory, and so then read from memory. And then, so yeah, I'm at the goal. So we are able to read from memory, and then now display 1 shape. Cool. That's the goal has been updated. Great success. And so then from here, now the hard stuff begins. Well, okay. So we have the kind of ugly bounding box, and so now we have all of that. Then parameter. I'm gonna set this out, and I can just have this be 0, and it's like whatever. And so then parameter. So now we read the bounding box, and now we can check the bounding box. So then we're going to do check bounding box. We'll just set that to 6. And so then if it fails the bounding box, I'm just going to say output 0, go back to the start of the output 0, and then just go to the next one. Then what we're going to do is parameter, and if we're in the bounding box, I'll just output the color, right? Parameter read color 1 is 7. Read color 2 will be 8, and read color 3 will be 9. Amazing. So read bounding box is there. I'll just yoink this, right? Yeah. So this goes all the way down to 106, and this is 77. So this should be 29 down. Paste. Yes, amazing. So read. Okay, so now down here, read color 1. Did I write this color? Read color 1, 2, and 3. And then here, read color 1. Color 2. And then here, color 3. And if counter, it's just 0, 1, and 2. And obviously we have the color up here. Yep. Color. 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 Cool. And if the counter is 2, then obviously we have an output color. Y2J. And I will set this to be output color, output color, output color. And at the end of our color, we're going to be incrementing the pixel and going on. So, and obviously, so then read shape bounding box 3. This will be going to check bounding box. Read shape bounding box 3, check bounding box. Check bounding box. Begin. End. Right, so begin, end, there we go. And so check bounding box. If, so obviously bounding box of 7 to 0 is, I'll have the if be the, no, we can't do Python stuff, so it's like whatever. If the bounding box, if the left end of the, so hold on, we should probably check from the pixel location, what do I call it? Current pixel, yep. Current pixel, pixel of 7 to 0, if it's less than the minimum on the bounding box, or, what? Or the, I'm gonna have this be on multiple lines. Current, I'll just, yeah, current pixel of 15 to, well no, this is still 7 to 0, is greater than the bounding box of, yeah, if it's greater than the bounding box of 15 to, what is it, 8, or, yank paste, get rid of that, begin, end, not, oh my god, not in bounding box. And here we're not going to do the whole fallback type stuff that we can do later. That's a next stream type thing. 15 to 8, 15 to 8, and then here we're going to go 23 to 16, 31 to 24. So if we're not in the bounding box, I'm just going to set the hello. Color will be 0. Next state will be, I call it right? I'm just going to use read and write. Yep, cool. Next state will be right color. Cool. And then, yeah, that's all we need. Else, then we're just gonna read the color. Begin. State. Read. Color. 1. Counter will be reset to 0. Cool. And so then here. So the output register. Oh, and then the address. Mem address. We're going to set that to mem address +1. Check bounding box. Yeah. And then here we're going to increment the address. And obviously there we're going to write the color. Yeah. And we're going to generate the pixel coordinates on the fly. Mem address +1. Yep. Hold on. Let me rename mem address to be read address. And then I will have a write address. Where is it? Yep. Here we're gonna have a write address. Here we're going to edit the write address, and then yep, everything else looks mostly good. And then read color. Yeah, so from here we're going to so read address. So yeah, we're going to read color, counter 0, read address is 0, and then so here's read color. So we go to the read address, we read it, color, right? Then next one, read color, cool. Increment 2, and then we edit the R, the G, and the B. And so otherwise, if we didn't finish all of these, we go back to read color, and then if we did, we go to write color 1. Write color 1. Yep. Cool. And then now we have to figure out. I'll just set this up in the first read shape bounding box thing for the, because this is the first state we're doing where we actually set up the current pixel, right? So we know the current pixel. We've incremented it in the final write color state, and then here now that we know, I mean we can always just do current pixel plus 1. Yeah. Okay. And so the starting write address should be, I should probably use hex, so 24 hex 8 1 2 2. Yep, there we go. It's all the way up there because that's 2 to the 23, and then cool. Now write color. I think that's the right number of lines. Let's find out. If counter equals to... it's not, but... we can just... these ones. Y3J. Paste that in. Cool. So, now we have a copy here. So this is going to be write color. And so it's going to go to the write address. The write address. Write address. Cool. And then we have all the stuff there. This is going to go to write color 2. Write color 3. Cool. And then, so we have the counter plus 1. Counter. I have to reset that. Cool. So, if counter is 0, then we have the output, right? So, UO out register. Yeah, we only care about UO out here. We're going to do this one at a time. UO out register will be not UI in. It will be color of the first set, so 7 to 0. Then it will be 15 to 8. Then it will be 23 to, and then it will be 23 to 16. Cool. So now we are outputting to the right place. And then what we're going to do is, if the final counter is done, so if it's not done, we're going to go back to write color is 1, and then the write address increments by 1. And that should just work. We can just go through, and then the current pixel right? The current pixel it just increments, right? Because x is a small one, and yeah, and then yeah, current pixel plus 1. I can just paste that in there. That always happens, and then no, sorry, this is current pixel. Current pixel. And then the state after this will go into check. It'll probably just go back to read shape. No, bounding box is set. Well, you probably want to just go to read shape bounding box 1, yeah. State goes into read state bounding box 1. Cool. Syntax errors. This is expected. This is expected. So, yeah, 113 has the syntax error. It's probably just lack of semicolon. Yup, it's lack of colon. 126. What's the issue here? $126 and $154. Okay, there's something about these specific lines that I copy pasted. But then how is this different from this? Read color 1, check bounding box. Begin. The ends are the same. Oh, there we go. Got end there, and then read color. This one doesn't end though. Cool. 115. 115 has an issue. 115. Cool, and then from here, it's just we fill this out, right? Maybe the parentheses make it better? No, it doesn't. One. Okay, sure. Okay, let me solve the one at 180 then, because I think the rest of those is downstream. The 181. Here, read state bounding box 1. Unable to bind read state bounding box 1. Huh. How did I fix that? Read state. Oh, hold on. I had to increment these numbers. 10, 11, 12. Read shape bounding box 1. There we go. The words are similar. The words are very similar, as you know. Cool. Now, current pixel. 14, 15, 16, 17. Yeah. $14, 15, 16, 17. Okay, yeah. If I have to do nested if statements, I will do nested if statements. Oh my god, I have to do nested if statements. Huh. Okay. Sure. First I have to edit the test.py. So write to memory. There was actually supposed to be 2 write to memory. Write to memory. I'll just set up, say, no. I'll just have a few. Yeah, I'll just say if data is not 0 as a quick and dirty check. So obviously we. Okay, hold on. So we read from memory, and then now we just have to have a whole bunch of weights, right? How much weights? So we need 1 for check bounding box, right? Await. What's the text? Await clock cycles. Yeah, cool. Right. So we're going to have a decent number of weights, right? So we're going to have so we'll wait 1 clock cycle to get into that first state, the check bounding box, and then we just go. And then here we should need to read from memory another 3. Right, so this will be 3 from memory address 5. Yes, in theory that should just work. And then await and write. 5, 3. Or so they should just start out at, and hold on, y is the bigger one here, and then x. Cool. Amazing. This is still failing. Await the write to memory. Okay, let's just do this for write to memory. Memory address write. Name data is not defined. It's in line 33. Oh, rip. That belongs up here. Cool. UO out value. So writing to memory address 34. What? Oh. So this is a crazy big number. Memory address, yes. And so byte 0, byte 1, byte 2. Yup, sounds about right. We're asserting we're trying to go there, modulo 256. So theoretically, we have a. Why are we trying to write to 34? Write to memory address 2 to the 32. Oh my god, that's XOR. I'm so good at this. Amazing. I love mixing up XOR with to the power of. Cool. There we go. And we have to write big number. Cool. DUT.UIO value equals output enable. What? Oh. Output enable. These should all be output enable. And we're not touching UIO OE. Okay. UIO OE. And then we just type this in, dut.uio.oe.value, and we read that. It's 255. Output enable, that's 255. Oh, UIO out. Oh, I didn't change that. Yes. VI. So that's how memory knows. That's how memory knows to actually edit it. So yeah, I forgot to edit that. Whoopsies. UIO output register. That's 0. Read still 0. Write should set this one as 255. All ones. Nice. UIO out dot value. Still having issues? UIO out reg. Oh, I had a delay by another one. At least in this state. Does that solve the problem? No, that doesn't. UIO out the value like immediately after? Hold on. What line? Line 50. This code is not that long actually. Line 50. It's the second one. It's the output enable one. Yeah. Yeah. So we know this one is correct because this should be 0. This one should be 0. So we know it's outputting 0 here and it's outputting 0 here, which is not what we want. Cool. Rip. I mean, okay, well, what we do is we just, we open up a GTK wave, and we open in a new tab. We go home, files, test, and then, is it GTKW? No, it crashed. No, it's VCD. We're looking for VCD. Whoopsies. Oh boy. Home, files, YouTube. And then from here we go this, test. Where's the VCD? Symboled? ITL? No. Podcast results. Where's the VCD? What? Requirements. Where is my VCD file? Hello? Make error 1. Yeah. Where's my VCD file output? Huh? Okay, well, sure. Where would my VCD file be? What's in the make file? Project sources, Verilog sources, yeah, that's all fine. Compile logs. Test, yep. Huh. Good Okay, this is kind of strange because we do not have a make file. Well, not a make file. We don't have a dedicated output thing. So that's strange. Kind of strange. Yeah, so now I just have to figure out how to handle all of this, right? So, okay, this is strange. Okay, so let me go into the test, right? Do we need the final clock cycle on waiting here? Right, so this effectively means we're in the output state, right? And we know the next, we're in the input state, and so we know the next state is what we want it to be. So I'm going to move this to the start of the thing. So, and I'll get rid of that. And let's see if that changes anything. The second read from memory fails. Come on, Coco TV. Why are you not giving me information? Come on. Okay. So what's the problem here? We're attempting to read memory address 1, but presumably I will paste this here. Memory address read And then this is going to be UO out. I didn't even write this all. Oh boy. UO out. What? Mem address? Oh, it's just called address here. Because the mem address calculation is above it. There we go. So a bunch of prints. Right, 0. And then it's still on 0. We need another cycle at the end. Right. To let things settle. So hold on. Let me... We need to remember we have this here. So we need a clock cycle at the start and a clock cycle at the end. Okay, well then I'll bring this back. Bring this back. Cool. And then on writing, right, so read. Writing the first byte. This is good. Let me yoink in the UO out line. So the problem is the actual data we're outputting. Bang. Right, cool. 0 or 1s, and then UIO out dot value equals output enable. What is UIO out dot value right now? UIO out UIO out, and I will paste it in here so we know what's going on. It's still 0, but here it's, yeah, UIO out is 0. Why is UIO? That's actually project.v. So why is UIO out still 0? UIO out reg. UIO out reg is read, yep. Right, UIO out reg turns into 225. That checks out. The address and stuff is all correct. We know this. And then up here, UIO out reg. Okay. UIO output enable. Okay, sure. 1 means output. So this is, we're trying to read. Why? Oh, I know the issue here. Your out value is memory line 53. Your out. Okay, so EI test.py line 53. Turn off caps lock. Whoops. Okay, what's going on here? UO out. Yup. That's correct. What is... And here, dib, long brackets, sure. Okay, so both of the right shift. The testing code is wrong. Amazing. Yeah, the testing code is wrong. What is 1, 2, 3, 4, 5, 6, 7, 8, 9? Why is this at the int limit? Oh. Hold on. What is the number? What is the number right shifted by 8? Okay. That feels wrong. It is mem address. Yeah. Okay, so right shift by 8 without moduloing it. Right shifted by 8, big number. Right shift by 16. We should just get the number we want. 65536. That's just a raw power of 2. That's wrong. Our expected is wrong. Yeah. So 2 to the 32? No. 24, man. 256, okay. So this is 2 to 23, whoops. Yep, okay, I think that's... Yep, and now the problem is data. So... And so you out value. So we have the stuff, and now we have to output the data. And so then we assert that this is equal to data. What is our data? And then, because if our data is wrong, we're cooked. Data. It should just be all data is 0. That is wrong. No, that is correct. What are we outputting here? That is wrong. UO out should be not that. Slash src file.v. Cool. And so then what we do here is we okay, so oh my god, this should be right. Okay, yeah, sick. Okay. We have a few warnings that I want to fix. In here, yep. Dot value. Cool. So, yep, we still fail here. Cool. So, UO out. Oh, we wrote the first 0 just fine. But the second memory address. Line 47. Okay, so from here, I just have to figure out how to get the memory address stuff working, right? So this is very much yeah, so now I just have to alright, well, it looks like we need more prints. The problem is at the start memory address thing, the minimum one. Okay, the one with all the prints. I really need to, whatever. Yeah, so this one works. This one we should see a 1, but we're not. So the problem is when we increment the right address is not going up. VI. Because we... That's an issue. Amazing. That's the 3 color right. And we're reading from address 1 now. Nice. UO out is 0. Why is UO out here 0? The address we should be reading should go back to 1 actually. If only I could see what happened to read address. Read address is permanently increases. Permanently increases. I'll just manually set read address to be equal to 1. Wait, read. Okay, so we outputted the proper colors. Right, so we did the bounding box check and we outputted the proper colors for the first pixel. Why is UO out 0? Okay. Where's my VCD file? qb.vcd. Where is my VCD file? What is in SimBuild? Oh my god, where's my VCD file? Come on, man. This is annoying. If it fails, it should tell me the VCD file. Where's the VCD? Coco TV not. Tiny tape out. Cool. Okay, so now we're just trying to find the VCD. Yeah, no VCD file dump. Yes. Cool. If Coco TV Sim dump file. Okay, hold on. This is Verilog. Nah. What? Make dash. Hold on. What if I just type make? It fails. VCD file. No VCD file. Okay, we gotta keep doing this manual print-based debugging. This is annoying. I can't just look at the signals. Sure. The problem is UO out is 0. So this means that we are, yep, 0, 1, 2, yep, that checks out. 0, and then 1, 2, 3, 4. We go all the way back to 0, which is not good. SSC probably V. Cool. Read address is 1. Read shape bounding box 1. Read shape bounding box 1. Read address of this. This should just output 1, because read address is 1. Yeah, read address is 1. Yeah, read shape bounding box 1. Read address gets set to 1. Current pixel increments by 1 when we're doing the bounding box checks. Yeah, that should just work. Sure, that's strange. And so, yeah, so we read 1 byte from these, and then we moved on. And then we read all the bytes, and we should be here. Do I need a little bit of a delay? VI, yank, paste. I mean, hold on. This right, we have an delay at the end. We have a delay at the end. Huh. I think this is a bug with the thing, but I'm... Dang. Okay, so... So... Cool. I really want my signal viewer, unironically. Sure. Leaving make had an issue. Results.xml. Leaving directory. Make had another issue. Okay, dang. And it's an insertion error. What if I just don't assert on the read? No, that's cheating. But we're not going to cheat on these tests. We're not going to delete the test to say that we passed. This is not happening. Okay, I'm going to delete the UIO output enable stuff because that's actually useless at this point. Okay, cool. Failing in the same spot. Memory address read, trying to read 1, but this is actually trying to read 0. Right, so we finish the write, and we go to read shape bounding box 1. We finish this write, and we go to read shape bounding box 1. We have read address, right? Great. And then we have read address, which is also 1 in both cases. Yes. Read shape bounding box 1. Read shape bounding box 1. Current pixel plus 1. Yeah, that's intentional. Huh. Why is this failing? Should be reading from 1. Memory address should be 1. Okay, what if I set read address to like 100? Does that actually affect the thing before we get there? No, it doesn't. Right, so that's where we know the issue is, right? We know the issue is that read address is getting reset somewhere in the middle. Okay, so we have read address there. Read address increments by 1 when we read all the colors. So read address we know is correct all the way down here. Right. Check bounding box. I should just move, I should just move the color is, oh my god, there's the issue. There's the issue. Read address equals, no, this we're always writing color. Right? We're always writing color, and when we write the color, we set read address to 1, which is correct. It's getting reset somewhere in the middle though. Where is going to read num shapes? Read num shapes 1, 1. Rest of these should just go to read bounding box, yeah? Read shape bounding box 1. We are going to read shape bounding box 1. Read address. Right, top one. Then we set it. If we reset it, yeah. If we go, yeah, that's outputting. Yep. We set it to 1 on read num shapes 3. Then we output it. Then we increment it, right? Because the bounding box check. And then we, if we're not in the bounding box, we increment it. And then, so if we're in the bounding box, then we increment it. If we're not in the bounding box, we just go to right color. Sure. Then, yep, we are outputting. We increment it. when we're reading the color for reading 3, that we know that works. And then if the counter is 2, right, so we've outputted 3 things, right, this is correct. We read shape bounding box equals 1. Yes. Let me just paste this in here and see what happens. Nothing happens. Why? Why did nothing happen? Read address and write address are both here. Huh. Okay. I need my VCD files, man. I need my VCD files. I'm gonna fix my VCD file issue. That's, I think, the thing. CocoaTB test. The file doesn't seem to be generated. When I want to dump, VI. Okay, let me just like set up the stuff. Product title. Image accelerator. Name. Discord. Cool. And then description. Image accelerator. Clock hertz. We are going to be going at crazy fast 20 megahertz. Tiles. This is going to be probably 2x2, hopefully. Yeah, and everything else we stay the same. Inputs. Input. Cool. Do not change YAML version. Yep. SFC project.v. Not project.v. Config.json. We shouldn't touch that. VI makefile. Includes CocoaTB's make rules. Okay, and then hello, I want to copy this text. Control-Shift-C. Control-Shift-V. Okay. It's, what is it? Shell CocoaTB-config. Shell CocoaTB-config. CocoaTB-config. --s makefiles. It's in the Python. Yes, it's in the virtual environment. Cool. I should probably do ub pip install -r. Just make sure I have everything. That's the stuff I didn't have. Now please tell me that this generates the VCD file. No, it doesn't. Okay, I don't have a VCD file. This is annoying. Though, this is telling me what the value should be. It should be 1. We know this. Just for context, so people know what I'm talking about. VCD files. Hold on. Let me pull open the things. Files. Walu to be 298A. Here. Test. tb.vcd. Right. We can just like look at the signals. Like you can be like, hey, all these signals. What do they look like? Hold on. This just go out a decent bit. Well, you can see them changing. Yeah, you can see. So we can like have stuff is happening. It's like great, it's amazing, cool. Yeah. Sure. This. Let me zoom out a bit because this text is minorly cooked. There we go. One more. Zoom out. Cool. Now you can see all the text, right? Where 0 equals int logic. It's a whole bunch of stuff. Yeah, I really want my VCD file. You know what? We're in a good state right now. I feel comfortable committing this to Git. Yeah. So, am I thinking? Yep. Commit. Read from memory works mostly now. And then commit. Push. Cool. It did push. Great success. Now Now we have to, yeah, get back to it. Dang. Call. Just edit info.md, adapt test bench. Okay, I want this to be me. Fat. Cat. How to... Yes, gate level simulation, sure. How to run RTL simulation. Yeah. Make dash B and then GK wave TB dot VCD TB dot GTKW. GTK wave did not open. Oh, hold on. Let me just edit the let me just make the test pass first, and then we have a VCD file. Maybe. %s/assert, and we replace that with hashtag assert on all of them, and then yeah. So then a whole bunch of print statements. I need to kill the print statements. Finish. Make file inc sim interrupt. Yeah, okay, sure. I'm deleting all of this logging because once I get the VCD working, I don't need any of this logging anymore. This logging was all... We don't want any of this logging. Cool. We just want the VCD file. Yeah, and this is going to take a little bit because I have made it in such a way where I have to render a full image for test 1, which is unfortunate. It is certainly running on this computer. It's one test. It's going to take a little bit. There we go. Pass. Where's the VCD file? Why is the VCD file not being made? Run. Simulator support. Yes. Make. That's fine. That works. Where is my VCD file? Run CocoTB. Yeah. Okay. Whatever. Test. Where is my VCD file, man? CocoTB modules is test. Yes. Then top level TB. Verilog. Yep. Icarus. MVVP. Running on iVerilog. Yep. Single shape test. Where is my VCD? Okay, hold on. If we go to the GitHub with the commit up, test failed. Oh, right, because the test failed. That's fine. Upload VCD. Bang. There's a VCD file. There's a VCD file. We're running this in the cloud, apparently. No VCD file. What? Okay, you know what? Looks like we okay. Yeah. Looks like we there's a bug in the default one I pulled, so I have to figure that out. Okay, sure. Hashtag assert/assert. Cool. Okay, yeah. I'm going to figure this out. Compile DGD test. so let me go to the template I took from. Yep, generated from this template. So this is the template. And so then if we go to test, make file, CocoaTB 2.0, and then let's look at the history of this file. What changed? At the start, this, I only care about this file. View code at this point. Yes. I want to see the diffs. I want to see the diffs. Okay. You know what? Sure. What changed here? Makefile. Module is the base name of the Python test file. Okay, what if I just... No, we know... It knows where it is. Units, unit. Okay, yeah, that's fine. This is all good. So it didn't break here. This 2 weeks ago, yeah. We know it was working at this point. What changed here? Compile logs -i $source directory. It moved it where it is. Sure. Okay, well then. Do I just revert the CocoaTB version? No. Okay, hold on. CocoaTB simulator support. VCD. How do I tell it to generate a VCD? FST is smaller. Waves equals 1. Okay, I just said make -b waves equals 1. Failed. Do we have a new file here? No, we do not. Oh, we do have tb.vcd. Nice. Okay. Nice. File. Open. New tab. We go home, and then files, and then this, test, tb.vcd, modified 1 minute ago. TB, I don't want any of the parameters, or the unused, but I want the rest of this. There's our clock cycles, cool. So where's our state? State 0, 1, 2, 3, 4, 5, 3, 4, 5, 3, 4, 5. Yep, this is the bounding box. 4 for the bounding box. 6, and then we skip forward. Yep, and then we go back to 3, 4, 5. Amazing. Read address. Bang. 1, 2, 0. Yep. 1, 2, 3, 4. Yep. 1. So read address is in fact 1. Then UO out is goes to 1 and then 0 and then goes to 1. What? Yeah, this is the top bit. Then since it's in this state, next output should be 1, but we die here, so we need to be checking it 1 cycle sooner. There we go. vi test.pipe. So let's make sure the reads are actually good and not like slop, right? As you do, we have to check that the reads are not slop. So await clock cycle. So we know we have a clock cycle in the middle here. If I get rid of this one, we obviously fail, as you know, we expected this will fail. Then we go here, we refresh, it dies a lot sooner. UI in, so state 0, right? Output 0, 0, 0, right? Well, we're feeding in 1. Yes, because yeah, it's delayed by 1. What fails here? The next cycle, where we, yeah, so we're outputting 0, and so then, well, the data is, hold on, let's check that the data we actually got was fine, because, again, we need to, yeah, what is the value for read address? That's fine. Hold on. What is the value for bounding box? 01, 02, 60. It only changes 3 times, not the. Bruh. Bounding box. I set this up as the wrong size. It should be 31 here. Cool. Where's bounding box? Append. Cool. 1, 2, 3, 4, 6, 2060, 2001. That's wrong. The data we're getting for the bounding box is just wrong. UIN. 20 is here. Ah. So it goes 0, 1. So 0, 1, 2. Right? And so UIN, we accurately match that. We don't want the delay at the end. That's the issue. The test is wrong. We get rid of this delay at the end. Move it to the start. Delete this. Dies way faster. This is the correct number. And so this tells us the num shapes. Num shapes should update here. What is the issue here? The issue is the memory address is wrong that we are attempting to read from. Right, so we go here. Then we have the starting read one. And then this one is wrong. Cool. Yes. So now we have to, so now, again, zoom in. So, read address is in fact 1. So, when we enter state 3, so the state is currently 3, and so the next state we know is 4. Right? Next state is state 4. Cool. So, so we know state 0, 1, 2, 3. Right, 0, 1, 2. Delayed by 1. So no, UIN. No, we need this earlier by 1. 0, 1. We need to pull this right earlier by 1. Hold on. So this whole thing, this starting wait doesn't particularly matter. So we go wait 1 cycle, whatever, and then address. We get the address we're getting 0, and then we have this one, right? Cool. And then from there we wait a clock cycle because this is. So we assert that it. Oh, this is when we actually know what's going on. Oh, whoops. I guess. Hold on. And we also need another. Whoops. Okay, now what's failed here? UIN dot So we know the output is the right value, and so within that clock cycle, we edit this value, and then we await the clock cycle. We await the last clock cycle. Wait, no, this means we have two. Hold on. Yep, what failed here this time? This UIN should be faster then, right? UIN.value equals data. Well, what if I move it up here? What happens? Oh my god. Make dash b waves is 1. There we go. Yeah, okay. Num shapes does properly update. This does in fact happen. Read address is set to 1. I mean, read address is set to 1 anyways here, right? Like, project.v. Oh, we had to set read address plus equals 1 earlier, so we should probably do that at the start of the read. Well, when we do this. So we should probably increment read address here. And then I should probably do that for all the reads. Right, yeah. Check bounding box. That doesn't matter here. And then here, I can basically guarantee it to happen if I put it in the bounding box here. Make that should be waves as 1. Read address is correct. So then, why is this not outputting the right number? UO out reg. Read address 7:0. Read address is correct here. 1, 2, 3, 4, 5, 6. Yep. We should be outputting 0, 1. Read address of 7:0. Read address 7:0. Yeah. 15:8. 23:16. Yeah, that's all correct. UO out reg. Oh, we have delayed by 1 more to see it. Yeah. Okay. Yeah, that checks out. So this, we have a delay. We have the delay at the start. What? Okay, hold on. So delay, bang, bang, here. So we effectively have a delay of 2. No. Well, that one doesn't matter. Right, so we start, we assume all the delays happen. 1, 2, 3, and then make. That is 2 is the last one. Yes, yes, yes. So we need to move this down by 1. And then, yeah, so from there, I have to figure out, yeah, so now from here I have to this is correct. Read address, num shapes does actually update here. And because read address is correct here, we should, when we get to state 3, when we get to state 3, which is read shape bounding box 1, read address is correct. We know read address is correct. 7:0. Huh. UO output enable. Okay, you know what? I'm just gonna. What is the problem here? Yeah, state 3. UO out, mem address, modulo 256, 1. One module, it should be 1. So why is the thing here not 1? What is the warning? The warning. Yeah, okay. Sure. Let me just edit the test.py and just comment out this particular assert, and let's, yeah, cool. So fails a little bit later. Oh, right, because we're only writing it out delayed. So, vi. What we need to do here is we need to move these up by 1. No, I don't want to do that. Yeah, that feels jank. We need to delay. We need to have 1 less. Hold on, no. When do we see? Right, so now the important question here is, when do we actually see the data that we should enter? Right, so this is correct. We go here and then it gets delayed by 1. Right. UO out. Yeah, that's whatever. 1, 2, 3. 1, 2. Right, so we know we're outputting. We're going to be outputting here during this. Bang, bang. Outputting here during this. Okay, so this is a timing thing, because we expect to have data in by this point. Okay. So what we need to do here is be a little bit cleverer with our data, like, strategy type thing. So we need we need the flow to be better here. Interesting. I mean, the easiest thing to do is just move all of this up by 1. That's going to be really hard. So what we're going to do is we're going to be checking it differently. Know what? No. I've been at this for 3 hours. The progress has been made. I think I'm going to end this here and continue next time. I will see you all later. Goodbye.